So welcome to my this linear algebra live session class. Okay, yeah. So before going to our today lecture, okay, I want to recall some things. Then I'll go to linear maps. Okay, so please tell me what is the definitions of line for arbitrary vector space. Yeah, please try to give the answer. Yeah, please try to. For at least for R2, what is the line? Fernandez, please try. I already mentioned in class, I think you missed it. Yeah.
So it is a vector space with dimension 1.
Yes.
So it is generated by a point like
Yeah. So
can
in
be any
R2,
reason.
what is the line? In R2, yeah, line passing through origin is take any non-zero point here. So it is generated by this element, this non-zero element. Okay. It is your RD. Is it? So line passing through origin in R2, it is of the form. And okay, is it okay or not?
Yes, sir. Okay.
Yeah, in R2, line is nothing but a one dimensional subspace, okay, of R2. It is of the form where D is your non-zero number. Okay, so if you take any arbitrary line, okay, take any arbitrary line L. Okay, this is your arbitrary line. Okay, so corresponding this line you will get one non-zero vector. Okay, suppose take this is your P. Okay, then join this line through origin. Okay, okay, is it fine? So it is looks like your this one. Okay, so corresponding every line you will get one vector. Okay, such that, please tell something. Yeah, this is your arbitrary line. Okay, what will be the form of L? This is nothing but a translation of this line or this one dimensional subspace. Is it or not? This L is nothing but a translation of this one dimensional subspace. I am correct or not? Take
Yes.
any, yeah, L1. Then what will the form of L? L is L1 plus RP. Is it okay or not? Yeah, please tell me
Okay,
everyone.
sir.
Everyone are agree with me? For any arbitrary line, okay, or is nothing but a translate of one dimensional subspace of R2. Is it fine? Risu,
Yes, sir.
Ravi Shankar?
सर फाइन बट सर मुझे लीनियर मैथ ज़्यादा पता नहीं है.
No, it is not linear map. I am going through only the definition of line. I'll go through later linear map after this definition of line. Is it fine or not? Is it
सर फाइन
convenient?
सर ये सिंबल सर पी और ये सिंबल कैसे लिखा सर पी का और इज इक्वल्स टू आर पी.
Oh, this is your one dimensional subspace. Okay, one dimensional subspace of R2. Okay, definitely one dimensional subspace of R2 means this vector space will generated by only one element. Okay, any non-zero, take any non-zero number. So this one dimensional subspace will generated by some element, take D. Okay, so what is the meaning of D? This is nothing but a alpha time D, where your alpha is belongs to R. Okay, then we can take this, we can write this one. Is fine right now?
Yes sir.
Yeah, so your one dimensional subspace of R2 is nothing but a line passing through origin. We already know this statement. I already mentioned this statement in my, I think one to previous lecture. Okay, so this is your nothing but a line passing through origin. Okay, so right now I am taking any arbitrary line, this is your any arbitrary line L. Okay, so my claim is corresponding this line will get one non-zero number, and if you consider this subspace, take this is your P, non-zero number belongs to R2. Consider this, consider the one dimensional subspace is generated by P, then we will get another line, okay, which is passing through origin and P. Okay, so my claim is this L is nothing but a translation of this vector space. Okay, translation of sorry, it is P, translation of this one means there, if you take one non-zero number here, okay, this will looks like your L1 plus P, where L1 belongs to L. Yeah, please tell me, is it fine or not?
Yes sir, fine.
For everyone it is convenient? 1 minute,
Yes, sir. It's fine.
I need some water. Okay, then I want to generalize this definition for any arbitrary vector space. Okay, okay, this is your proper definition. Okay, so I will try to generalize this concept. Okay, oh my god, yeah, I want to generalize your this concept. Okay, so take let V be a vector space. Okay, V be a vector space. Okay, and take one non-zero number, write like that. Okay, oh my god, yeah, 0, take any non-zero number from V. Okay, so a line passing through P belongs to V. Okay, and having direction D is denoted by L P comma D, okay, and defined as there exists T belongs to R such that V can be written as this form, okay, means this is nothing but a your P plus RD. Yeah, try to compare these two definitions. Here we are talking about line passing through this point L1, okay. This line your this L line is was passing through your L1 point, and in which direction? In your P directions, okay. Here your V was any arbitrary vector space. We are taking any non-zero number, okay. So sorry. So a line passing through P, like a line passing through your L1, okay, same things. A line passing through P belongs to your vector space and having the direction D, okay, is denoted by these notations and defined as such vector V, okay, from your vector main vector space. There exists T belongs to R such that V can be written as P plus TD. This is your one dimensional subspace, okay. So yeah, this is looks like P plus RD, where P is the line passing through that point P and D is the in directions, okay. Is it fine? Is it similar to the same definition, this one? Please tell me, is it fine or not? Everyone are confident with this definition?
Fine, sir. Fine, sir.
Okay. So if you want, you can verify, okay. So take your Rn, okay. So take any arbitrary point P, okay. I am take we are familiar with notation X, so I am taking X, okay. Take x1 x2 up to xn, okay, and take D the direction. It's fine, okay. What will be the definition of line in Rn? Line in Rn is looks like this one, okay. These definitions, okay. This is your x plus RD, okay, or means x plus take TD, okay. Your T belongs to R, okay. Is it fine?
Yes, sir.
Yeah.
Yes.
So yeah, what we'll get? We'll get x1 plus T1 D1, x2 plus T2 D2, okay. Is it fine? Is it fine? Please tell me.
Yes, sir.
Yeah. So take this is yeah.
So your T will remain same in each tuple, no?
Oh,
Inside
sorry,
the
sorry,
tuple,
sorry,
that
sorry.
each
Yeah,
part T
yeah,
will
yeah,
remain
yeah.
the same.
Yeah, sorry. Sorry, your yeah. Thank you. X D1 X. Yeah, it's good. Okay, so this is your definition of line in Rn. Okay, take this is as a like P1, P2 up to Pn equal to this one, x1 plus Td1, okay, x2 plus Td2, xn plus Tdn. So equate both sides, okay. So we will get P1 equal to x1 plus T21 up to Pn equal to xn plus Tdn. Okay, so eliminate this T, then what will get? T equal to P1 minus x1 by d1, okay, P2 minus x2 by d2, Pn minus xn by your dn. So I think everyone are familiar with this definition of line in Rn. I am correct? Everyone are familiar with this definition or not? Please tell me.
Yes, sir.
Yeah, so this is passing through your x1, x2, xn. This line is passing through that one, and which direction? In the d1, d2, dn directions. Okay, this is the direction cosines of this line. Okay, you can check it for n equal to 2, n equal to 3. For n equal to 2, we'll get y equal to mx plus c. Okay, so please tell me, it is fine for everyone, this definition of line for arbitrary vector space?
Yes, sir.
Hans? Ravi?
Yes, sir. Fine. Yes, sir.
Okay, very good, sounds good. Yeah, so right now I am going to the definition of linear map. Okay, so yeah, please tell me what is the linear map and what is the history behind this map. Okay, what is the basic difference of a linear map from any arbitrary map? Oh, please tell me. Yeah, I think everyone know about the definition of linear map, but I am asking what is the difference between linear map and any arbitrary map?
Sir, a linear map will be with 1 degree equation like from domain to range we have a function and there is a mapping is there.
What is the difference between linear map and an arbitrary map? And what is the importance of this map? Why we are talking about this map? Okay. What is the special property? What is the special power of linear map?
So a linear map no is a function from a vector space to another vector space no, which this preserves the operation of the vector space.
Yeah. So it's a good answer. So yeah, if I am taking, I'm giving your arbitrary sets, okay, x and y. Take two arbitrary sets, it's x and y, okay. And when we are talking about functions from x to y, okay, so there is no restriction. This function, if you satisfy the definition of function, it's enough. There is no restriction on x, no restriction on y, no restriction on f, okay. So for the reason this function don't have any special property, okay. So when we are talking about some special functions, like here we are talking about linear map, he has some special power of this map, okay. So but for this need we need some extra conditions. We have to impose some extra condition on x and as well as y, okay. Then we can define some special map, okay. So please tell me which condition we have to impose on x and y. Please tell me. When we are
So this would be non-zero vector space, no?
yeah, this should, if you take 0, then we have to define the only zero element, zero map, okay. So here we want to impose one extra condition that x and y are vector space, okay. So why we are taking the x and domain and codomain both are vector space, I'll give the answer little bit later, okay. Here I am taking both are vector space, okay. Okay, is it fine?
Yes, sir.
Yes, sir.
Yeah. So if I am define any functions from x to y, any functions, okay. So these functions could we have any special property? Maximum it can be bijection. This is one good functions we know already, or differential or smooth. But I need little bit uh, good functions. This is also very good. Continuous function, differential functions is very good, but I need little bit more than this one. Which will pitch up some good property of this vector space. Okay. Normally, if you take any arbitrary functions, they can't preserve the algebraic properties of x. Okay. If you take any arbitrary functions, take f of x equal to x square from this two vector space. So this function, if you verify that this function can't preserve the algebraic property of x and y, okay, sorry, algebraic property of x, this function can't be preserved. But this is a very well known and good functions. This is also, but we are talking about little bit specific functions. Okay. Yeah. So we are talking about linear map. Okay. For this map we need the domain and codomain both are vector space, okay, which will preserve your algebraic property of x. Okay. So what is the importance of a linear map? It will preserve the algebraic property of a vector space. Okay. Is it fine?
Yes,
Both
sir.
vector space have the same field.
Yeah, sorry, yeah, I have to mention, yeah, it is over same field. X vector space, y vector, both are on same field. Take any field k. It's very good questions. And okay, so oh, you have to take the same vector field. Okay, so how we can define the linear map? Please tell me, someone. What is the definition of linear map? Yeah, please try to define the linear map.
Sir, f of u plus v is f of u plus f of v.
T of u plus T of v. Okay, for all u v belongs to x, it's fine.
And
After
sir,
that,
t of kv is equals to k times t of v.
kv is equal to k times T of v for all your k belongs to the field k. Okay. Another, these two is enough or we need another?
Sir, f of 0 is 0.
Mm. Yeah, this is your v, this is your, okay. Yeah, so this third one from 2 we can imply this third one. Okay, but this is also one important property of linear map. So here we can, if you see the definitions of a linear map, you can observe that this is your operation on x. Okay, this is also your operation on y. So when we are adding two vector in x, okay, taking image of that two vector, we will get tu plus tv, okay, with this addition on y. So here your map is preserve the if you take call is addition, the addition structure. Okay, and here is preserve your multiplication structure. Okay. So in one field we already know that in one field two operation is there. One is your addition operation, one is your multiplication operation. So linear map are preserving your addition operation as well as your multiplication operation. Okay, so for the reason we was telling that linear map is preserve your algebraic property of vector space. Okay, is it fine for everyone? Please tell me, is it fine or not?
Yes, sir, fine.
Yeah, so what is the geometric and what is the needed of x and y both are vector space? Please tell me right now you have to definitely you should give the answer. Why you choose the domain and codomain specific? Both are vector space. Please try to observe from the definitions. We are
So
talking about,
u,
yeah, please tell, yeah,
so u plus v should belong to x. That's why it's
yeah.
there, and scalar times of v should also belong to x.
And yeah, when are you talking about when we are seeing the image of this one, that time also your tu plus tv should be belongs to your y, and scalar multiple of t of v also should be in y. So for this special map we need the special structure of x and y both. Okay, so for the reason we have to take the x and y both are vector space. Okay, so what is the geometrical interpretation of linear map? Please try to give the answer. Sorry. Geometrically, what we can say about this map? Yeah, if you want to combine these two definition in single sentence, what? Yeah, I am going to definitely this one. Before that, I should write like that. If you can write like that, your u plus beta definition of linear map. Yeah, is it fine for all uv belongs to your vector space? Okay, and your alpha beta belongs to your the field. Okay, so we can write the definition of linear map with this single okay, okay, is it fine or not? If you combine these two you will get this one. Okay, please tell me, is it fine or not?
Yes, sir, fine.
Yeah,
Sir, combining 1 and
Yes,
2
sir,
will
fine.
give 3, right?
yeah, this no, yeah, no, is it fine? But I am telling about that this definition is fine or not. If I tell that one map from your x to y is satisfy this property, then we can say that t is a linear map. This definition is fine. This definition is enough or not? I am telling about.
Ah, yes, sir, it is correct now.
Yeah, it is correct.
Yes, yes.
Combine these two, you will get this one. So please try to give the answer. What is the geometrical meaning of linear map? Please try to look here. Take alpha equal to 1. Then what will get? You will get u plus beta v, where you take v is also non-zero. No issue. Okay. Then what will get? You will get tu plus beta into your tv. Okay. Yeah. Please. This is what is this? This one. If you fixed your u and vary v, okay, v belongs to v, and fix your u. What is this one? This is nothing but your yeah, take field K here, okay. Oh, when you're talking about take K equal to R, then what you'll get? This one. What is the meaning of this one?
A line.
Yeah,
A
line.
line.
Yeah. So geometrically, what we can say? We can say that linear map sends line passing through origin to line. Okay. Is it fine?
Okay, sir. Sir,
Okay.
please once again repeat, sir.
What is the geometrical meaning of what geometrically we can say for linear map? Please tell me.
Sir, it's a line, no? U plus RB we have got.
Yeah. This is the definition of line. Okay. So, but when we are talking about linear map, okay, so every time we are thinking about the domain is your vector space, okay. So this your can't be any line, it can't be any line. This is line passing through origin. You have to take u also equal to 0, okay, because otherwise if you take any linear map, we can't talk about this line. Only we can talk about this line, because you have to goes through this property, okay. So linear map, it sends line passing through origin to line passing through origin or to 0, okay. It can map the line to a 0 also, okay. These two things, linear map sends line to line or origin. This is the geometrically you can say for linear map, okay.
Yes, sir. A transformation of line.
Yeah, it transfer one line to a line or 0, okay. Is it fine for everyone?
Yes, sir. Fine.
Fernandez,
Yes, sir, fine.
Risu, yeah, Risu, is it fine?
Yes, sir.
Okay, so please give me one non-trivial example of linear map. I'm expecting from you. Yeah, please tell me. Interesting, definitely. So please give me one example of linear map. Okay.
So this projection of a vector,
Yeah, we can take
projection of
projection.
two-dimensional vector on one dimension.
Okay, it's very good. Yeah. Its linear maps looks like that. Okay. Take this is your any arbitrary point. Okay, xy. Take, yeah, this one xy. Take the projection on here. Okay, you will get x0. This is the property of linear map. This, sorry, not property, this is the special property for this one only. This is a projection map, we call this projection map, okay. So you can verify that this is a linear map, okay. So what is the special property of this one? This will send your any arbitrary point to your x-axis, okay. You can verify this is a linear map, okay. Another example, we can generalize also this one like that. And yeah, please tell me. So yeah, here is your domain is R2. Yeah, codomain is also R2. Okay, but what is the image of this one? This projection map. What is the image of this one? Yeah. What is the what we can say that the image of this one? This is also vector space. I'm agree. Okay, but what we can say about others property of this vector space?
So its image will be R.
Yeah, we can not say like that, because R special is not a subspace of R2, because R is only one coordinate is there, in R2 is two coordinate, okay. But when we take component 0, that time we can say R is a subspace of R2. Okay, so for one subset will, for subspace, that R should be your subset of R2, but R is not a subset of R2. R is a subset of R2, is it?
No, sir.
Yeah. So when we are talking about R comma 0, that time it's a subspace of R2, because here R2 had two components but R has only one component. Okay, but you can think like R. Okay, but because same property has this R comma 0 and R has same property. Okay, this is your one dimensional subspace, this is also one dimensional subspace. So what we can say about image of R2, this is nothing but a one dimensional subspace. Okay, subspace of R2, and it is also a line passing through origin. Okay, your x-axis. Okay, so please you can generalize this one like that. Take your oh my god, n is greater or equal to m. Okay, we can easily generalize this one. x1 x2 up to your xm. Okay, after that all are 0. Yeah, your t map from Rn to Rn. Okay, yeah, basically these two are isomorphically, these two are same. Okay, yeah, these two have same properties, R and R comma 0. Here also, this is what is the image of your t Rn, is nothing but like, yeah, is it? We can say this one only. Okay,
Okay, sir.
yeah, okay, and so yeah, so this is your t from take R to R. Can you tell me what is the form of linear map? Find all linear map from R to R. Your question is find all linear maps from R to R. This is your questions. Yeah, please try to. Anyone, do you know the answer of these questions?
So one of them is identity map. That is t of x is equal to x.
Okay, another one. I agree. Another, I am talking about find all. Okay, this is one particular example. I agree. This is a linear map. Also 0 is trivially you can take t of x equal to 0. This is also you can take. Yeah, this is your 1, this is your 2, but I am talking about all linear map from R to R. So after finding that map, if you put particular value, we will get this map, whatever you are talking. So anyone, do you know the answer of this question? Please tell me. Yes or no?
T of x is equal to some constant times x, where that constant is in the field.
T of x equal to you are sending to take alpha. Okay, alpha into x.
X.
Okay, for your alpha is fixed or it will vary?
it is vary.
In one's time it will vary, then it is too difficult na. So suppose it is varying, so take one here, one is belongs to R, that time many image you will get where vary, when your alpha will be vary, alpha into 1, alpha into 1, this is varying, so we can put here alpha equal to 1, okay. 2, if your alpha is vary it will be difficult, 2 into 1, 3 into 1, so it can't be map. Is the definition of it is satisfy the definition of map? So linear map
No.
at first it's have to be a map. You can tell like that, okay. Alpha you will be fixed, okay. Up then you will take this is your map, okay. When I'm talking about all collections, that time you will tell like that, okay.
I was trying to actually tell it in general, like the collection of maps are standard.
Yeah, I understood, okay. When we are talking about all linear map, that time will vary, okay, but for particular one linear map this is fixed, okay, like that. T of take T of x equal to 1 into x, yeah, this is one linear map, this is another 2 into x, okay, this is another linear map, check this one, this is another linear map, okay. So when we will put particular value of alpha, then we will get linear map, but when we are varying it not be a map, okay. But when we are talking about all collection, that time we will say like that, yeah. Will when we are talking about this all linear map, okay, all linear map, that time we can say like that, okay. T of x equal to alpha x, okay, for all alpha. When we are talking all linear map, for that time we will say only all alpha, okay. But for all alpha we will get one sorry, for particular alpha we will get one linear map, another particular value of alpha will get another linear map, okay. But for one particular linear map we can vary the alpha, okay. When collecting all linear map, that time we can say for all alpha, otherwise we can say for one particular map this alpha is fixed, okay. Is it okay for everyone?
Sir.
Yes, sir, fine.
Yes, sir.
What is the proof of this one?
Sir.
I am agree. This is your all collection of linear map. But what is the proof? I need the proof. Yeah, please tell me. Please tell me what is the proof of this one. So what?
You have to,
Please
so you
tell.
have to show that T is a linear map, no? And if you take any other map, no, then it will be same as that only map.
Yeah. So what is the proof of? I am asking about proof. You have one arbitrary map from T R to R. So you are telling that it will form of x where your alpha is fixed, okay. Yeah, for all x belongs to R. I am asking about proof of this your statement. Your statement is correct. This is the collection of all linear map. If you vary alpha, we'll get all linear map. Yeah, I'm agree. But what is the proof of this one? Why all linear map looks like this one? Please tell.
Sir, let me take two non-zero elements from R, X and Y. and we put t of x plus y as a map, then as an image of it we can take as t of x plus t of y, and
Okay.
after that we can write t of x as a alpha of x plus alpha of y. Then we can common alpha and
No,
alpha
yeah.
x plus
1 minute,
y.
Disu, please. This is a linear map. I agree. My question is, why all linear map looks like this form? Understand my question, Disu? Yeah,
So
I'm
now
agree.
I understand. Yes, sir.
Yeah, I'm agree. This is a linear map. You can check. You can verify in.
Sir, addition is preserved, na, in a linear map.
Definitely.
So we will have of this form.
Yeah,
So
but
because it represents the equation of a line, that's why.
yeah, you are approaching to 100% correct. Please precisely tell. Yeah, you are correct. I agree. Yeah, so this is your one dimensional subspace. So it will be generated by some vector. Take R is generated by, okay, some non-zero number. Yeah, 100 is your concept is 100% correct, but you have to write precisely when you are going to some interview. Yeah, they will appreciate your answer. It is preserved line, and in R, line means only R. Okay. So there is nothing any other subspace of proper subspace of R. So precisely, if you want to write, how you will write, take your any non-zero number from, okay, R. So this will be generated by, R is generated by this one. Is it fine? So means x0 is a basis of R. Is it fine? We can write this one or not? Please tell me.
Yes, we can write that way, sir.
Yeah. So take any linear map. Okay. This is the arbitrary linear map. Okay. So what we have to show? We have to show that t of x equal to some constant into your t of x. This is your our m. Okay. Your, this is for all x belongs to R. Okay. For all x belongs to R, this is x0's basis. So we can write x is alpha into x0. Is it? We can write. Can we write or not? Your x is your arbitrary element from R. Can we write any element of, an arbitrary element of R is linear combination of, oh sorry, is scalar of scalar multiple of x0, because your x0 is a basis of R.
Yes, sir, you can write.
Yes, sir, we
Yeah.
can do that.
So try to find the image of x. Yeah, this is a linear map. So alpha will come out, okay? T of x0, okay? Is it fine? Please tell me, is it fine or not?
Yes, sir, it's fine.
Yes, sir.
So after that, what should I do? Please tell. Yeah, you can take, this is your sum y0, okay? Yeah, please tell me after that. And we can think this is one is there, okay? So take its out. Okay, no issue, no issue. We should not write like that. Okay, so 1 minute. Your alpha into y0 is fine. After that, we have to looking for constant into x. Okay. How we can write this is like 1 minute. Okay, so till now is fine. Yeah, so we can choose this x0 is 1. No, take this is, we can choose this one or not. R is generated by 1. We can write this one.
Yes, sir.
Yeah, so your x0 is 1. So we can write x is like that, alpha into x0 means alpha into 1 equal to alpha. Okay, so here what we will get, x equal to your alpha into t of 1. Okay, and your alpha is your x, so we will get, since these are two real number, we can commute. Okay, so t1 into alpha, take this is your constant c. Okay, and this is your x. Okay, yeah, so we are getting t of x equal to some constant into x for all x belongs to R. Is it fine? We are taking x0 equal to 1. Okay, so we can think the 1 is the basis of R. Is it fine or not? 1 is the basis of R. Is it fine?
Yes, sir, it's fine.
For everyone?
Yes, sir. Fine.
So take your x0 equal to 1. So we can write x equal to alpha into x0 means alpha into 1 equal to alpha for all alpha belongs to R. Okay, so we are taking the image of x. Okay, so what will we get, alpha into t of 1. Okay, what is the, take this is your constant c and alpha equal to x, you already know from here. Okay, so we can write t of x equal to constant into x. So here we are considering the any arbitrary linear map. Okay, from R to R we are getting any arbitrary linear map, it looks like this one, t of x equal to some constant into x. Okay, is it fine? Is it fine or not?
Yes, sir, fine.
Yeah, so only trick is we are if any linear map, if you know that one map on the basis of the vector space, what is the image of one linear map on the basis of vector space, then we know the full linear map. This is the concept here I have used. Okay, so I started with the one basis of R. Okay, so we can generalize this concept for any arbitrary vector space. If we know what is the image of one map on linear map on the basis, then we done. Okay, is it fine for everyone?
Yes, sir.
Yeah, so today I don't have much more time, I have to stop here. So do you have any questions, please tell me. Okay,
Sir, here one is the